Hi everyone, today I'd like to discuss something known as a chemical equation. Now if you're watching this video, you've probably already seen something like this. But today we're going to get into how to interpret this, particularly numbers like coefficients versus subscripts. What do those mean on a chemical level? And then we'll close by talking about the mole ratio. So let's start with a very simple equation and go over how to interpret this, starting with the reactant side. Now we'll interpret these two H's as representing two individual hydrogen atoms. And by individual, I mean we can imagine that these two hydrogen atoms move independently from one another. They march to the beat of their own drum. See how each of their motions had absolutely nothing to do with one another. Now what this reaction tells us is that if these two hydrogens were to come together and form a bond, as it's called, this produces the chemical H2. Now that these two hydrogens are bonded together, they will move around together as a unit, like so. And we call this unit a molecule, i.e. two or more atoms bonded together. And notice that the motion of those two hydrogen atoms when bonded together is very different from when they're completely independent from one another. Now I do want to clarify a few things for the sake of accuracy. First of all, the bond that connects the two atoms is rather abstract. It's just an attraction between the two. There's no physical rope or like rubber band-like thing connecting the two together. That's just how we visually represent it in a chemistry class because it's nice and simple. Second of all, I don't want you to think that when these two atoms that are bonded together are moving around, they are as rigid as I'm making it seem in that animation. In fact, even as they're moving together as a unit, they are moving back and forth from each other, they're rotating around, but for the sake of simplicity, I'm just going to represent the motion like this, nice and rigidly, to really emphasize that they are ultimately moving together. But really, it's like the difference between two people walking together holding hands, where they do move relative to one another, but due to mutual attraction, they're mostly moving together, as opposed to two completely independent people. Which is more like the individual atom scenario. Now it's this subscript here that tells me that these two hydrogens are bonded together to form this unit known as a molecule. This brings us to the concept of subscripts versus coefficients. Now to understand coefficients, let's think mathematically. And I'm going to shift our focus back to the reactant side of things. Now in math, we know that if we were to write 3 plus 3, well, that's really the same as just saying 2 times 3, right? So similarly, with a chemical equation, if I say hydrogen atom plus hydrogen atom, I could represent that as simply 2H. And so I could rewrite the equation we've been looking at this whole time as being 2H yields H2. It means the exact same thing, it's just a little bit more compact. And I could technically also include a coefficient in front of the H2 and just say that we produce one of them. But we don't really do that, just like we wouldn't write 1 times 3 typically in a math class. We would just say 3. I'm going to erase that last bit so it doesn't get too cluttered here. And I'll wrap up this slide by quickly saying that this equation here just means what we've been discussing. Two individual hydrogen atoms come together to form one H2 molecule. And if I wrote that same equation backwards, like H2 goes to 2H, well, that would mean the exact opposite happens. A single H2 molecule is breaking apart to give two independent hydrogen atoms. Now let's get a bit more complicated and combine subscripts and coefficients. So imagine we had this equation. How do we interpret this? Well, let's start on the reactant side again. So this 2 subscript here means the same thing it did in the previous slide. It means we have two hydrogen atoms bonded together, and these two hydrogen atoms will move together as a unit. But we also have a 2 coefficient, which means the same thing it did before, that we have two of these hydrogen molecules, and each of these molecules will move independently from one another. And finally, since there's no coefficient, we interpret this part to mean we have one oxygen molecule consisting of two oxygen atoms bonded together. And so we can imagine that the situation looks something like this. Notice that all three molecules are moving independently from one another, but the atoms that are bonded within those molecules were moving together. As a quick aside for accuracy's sake, eventually you'll get into bonding theory and you'll learn about double bonds, and you'll realize that I should really have two lines connecting those oxygen atoms in an O2 molecule, but we really don't need to touch that for today's purpose, so let's not go there. Now let's deal with the reaction itself. Imagine that these reactants all meet, and bonds that are connecting all these atoms together break, and new ones are forged like so. How that happens is a topic for later in your chemistry class, but for now just notice what we have here visually and how it matches our product in our chemical equation. We have two individual units that each consist of two H's and a single O, all bonded together to form a molecule known as H2O, which of course is water. And we can imagine that this molecule can move independently from this molecule. But again, all of the atoms within the molecule will largely be moving together. So hopefully at this point, the difference between a subscript and a coefficient is clear. Now the coefficients also inform us about something known as the mole ratio. So let's get into that. So far, we've only covered the smallest amount of reactants to make this reaction go. In other words, two H2 molecules meets one O2 molecule. But in principle, we could have twice as many of each of those starting reactants, and thus get twice as much product. So here we could imagine that we started with 4 different H2 molecules and 2 different O2 molecules, and ultimately produced 4 different H2O molecules. So to summarize, it's like I had 4 H2s, 2 O2s, and I produced 4 H2Os. Well, at the end of the day, the ratio between these three numbers is identical to the ratio of our coefficients, right? We have twice as many H2s to start with as O2s, and we produce twice as many waters at the end as we had O2s. Or we could say we have the same amount of H2Os at the end as we have H2s to start, which agrees with the fact that they have the same coefficient. And this ratio will always hold true, regardless of how many O2s I have. So long as I have twice as many H2s, they can combine together and form twice as many H2Os at the end. So let's say I scale up a little bit, and I have a dozen O2 molecules and 2 dozen H2 molecules. Feel free to pause and count for yourself. Well, we could get them to all react and yield 2 dozen H2O molecules. Now I use the term dozen for good reason. We know that dozen is just a word that means a number, i.e. 12. Well, in chemistry, we have a different word. It's mole, and that's just a word that means the number 6.022 times 10 to the 23rd, or what we would call Avogadro's number. And so let's shift our focus from having dozens of molecules to moles of molecules. Let's say we had 6.022 times 10 to the 23rd O2 molecules, or in other words, 1 mole of O2 molecules. And we had twice that many molecules of H2, which is really this number here, but who wants to say 1.204 times 10 to the 24th? That number is gigantic, we can't really comprehend it. Much easier to just say that's 2 moles worth of H2 molecules. Well, if all of those molecules came together and reacted, we could produce 2 times 6.022 times 10 to the 23rd H2O molecules, in other words, 2 moles of H2O. Now, I am not going to try to draw that many molecules in PowerPoint, or my computer would go. Now, I'll close by just summing up why it's called a mole ratio. Ratio in this case means that we're referring to the relative amounts of reactants and products involved in a reaction as we've been seeing. Moles, because we typically are dealing with these large amounts of atoms and molecules, and so it makes more sense to think in terms of moles. That being said, we don't have to talk about moles. We could just describe a few dozen molecules, or even just a couple of individual atoms. And I think that's one of the confusing parts of that term for some students, is that we think that it has to always be about moles and that there are these different types of ratios. No. At the end of the day, the mole ratio ultimately just states that if you have twice as much H2 as you have of O2, notice I'm including that one coefficient to be very specific, you can produce twice as much of H2O as you have of O2, regardless of if that means that you have two individual molecules of H2 and one individual molecule of O2, 2 dozen molecules of H2 and 1 dozen molecules of O2, 2 whole moles of H2 and 1 mole of O2, or 20 moles of H2 and 10 moles of O2, in which case you would get 20 moles of H2O as a result. The mole ratio is ultimately just describing the relative numbers of reactants needed to form products. And since we typically talk about moles in chemistry rather than just a few atoms or molecules, it makes sense to call this the mole ratio. Now later in your chemistry class, you're going to learn about limiting reactants, which adds another layer of complexity to the math associated with these equations. But even when you get there, the logic of what subscripts and coefficients and mole ratios mean will be exactly the same as what I covered here. So hopefully it all makes sense, and I'll see you again soon.